In the second part of lecture 24, I am actually going to solve a linear elasticity problem with two elements. This is the same mesh that I had for the first problem that was just about interpolating displacements and strains. So here we actually have only two, we know the displacement for only two nodes. So nodes 1 and 2 are fixed, both in x and y. So we know the displacement is 0, 0 for both of them. But we don't know the displacement for nodes, global node numbers 3 and 4. And we are given some details about the material properties, Young's modulus and Poisson ratio, and we are also told that there's a constant body force due to gravity, and we can approximate it based on this. This should actually be plus gravity times thickness times density, because I'm having the negative right here. And then what we need to do to solve this problem is compute the stiffness matrix for each element, then assemble the global stiffness matrix, compute the force vector for each element, and assemble the global force vector. And finally, set up the system of equations and solve for the unknown displacements. One thing that I forgot to mention when I was explaining the setup of the problem, these two nodes right here, nodes 3 and 4, if they don't have essential boundary conditions, that means that they have natural boundary conditions. But in this case, because there's no forces acting on those nodes, that means that these have natural boundary conditions, but with traction equals 0, the 0 vector. So they have boundary conditions. It's just that they have a 0 force boundary condition. All right. For this particular example, I'm not gonna solve everything because it would take a long time to do all the calculations by hand. And instead, what I did is I created a Python notebook where I solve this with Python. So I'm gonna sketch out the solution, but not going to do any of the calculations in this video. But you can check out the Python notebook to see the actual numbers. So in order to assemble the system of equations, we're going to do the thing that we always do, which is we have the mesh and everything. We're going to do part A, which is we need the stiffness matrix for the two elements. And if you recall the definition of the stiffness matrix, so for element 1, this definition is true always. So this will be the integral over the element, so the integral of the first triangle of the B matrix transpose times this D matrix times BE over the triangle. Right, so this is the integral that we will need to do. And if you remember from the lecture on Monday, the B matrix for the, well, I guess, the B matrix in general, so these are all matrices, just to recap, the B matrix in general is a 3 by 2 times number of nodes, 3 times 2 times number of nodes matrix, which has partial derivatives. So this will be first shape function with respect to x, then 0, then first shape function with respect to y, 0, first shape function with respect to y, first shape function with respect to x, then second shape function with respect to x, 0, second shape function with respect to y, and so on. So this is a pattern that we wrote down at some point in the lecture on Monday, or probably Friday of last week. So this is true for any element, and in particular for the triangular element, you can work out the exact shape of this B matrix given the definition of the shape functions. So this is for any element. This is also for any element. And this is only for the triangle. So for the triangle, because you know the definition of the shape functions and you can take the derivatives, then, and it's constant, then you just have 1 over 2 times the area, and this looks something like this. So this has y2 minus y3, 0 y3 minus 1 y1, 0 y1 minus 1 y2, 0, and then 0 x3 minus x2, 0 x1 minus x3, 0 and x2 minus x1. And then at the bottom here is basically just intercalated, so this will be x3 minus x2 and y2 minus y3, and this will be x1 minus x3, y3 minus y1, x2 minus x1, y1 minus y2. And you can look it up, you don't have to memorize this. So this will be the B matrix for the triangular element. So for the first element, because we know this is the local node number 1, 2, and 3, then you can go ahead and calculate what is the x1, y1, x2, y2, x3, y3, and calculate the area of the triangle, and then plug that here, and then you will get your B matrix. So that's how you will get the B matrix. Then the D matrix, that I also wrote this one last time in the lecture, so that just depends on the material properties for plane stress, which is what we are asked to do. This one just looks like E, so Young's modulus over 1 minus nu square times 1 nu 0 nu 1 0 and 0 0 1 minus nu over 2. Again, this is given, you can look this up in the book. So now we have the definition of the B matrix, the definition of the D. If you actually want the numbers, just get the coordinates of the nodes, plug them into the B matrix, then you get the definition of the B matrix. If you actually want the numbers for the D matrix, just plug in the values. And then the key point is doing the integral. But because these are all constant, you don't really need to do the integral. So for the triangle, this is just the area of the triangle times the B transpose times D times BE. So for the triangle, no integral, just multiply by the area. And then this B matrix, like you can see here, it's a 3 by 6 matrix. So if you transpose it, you get a 6 by 3 times a 3 by 3 times a 6 by 3, 3 by 6, then you get a 6 by 6 matrix. And you can do this in Python or MATLAB. And that I'm not writing it here. You can look up the code. So this will give you a 6 by 6 matrix. Now the important thing is actually the assembly. So I do want to do that. So for the assembly, so this K1 matrix is just the contribution of the K1 to the global K. And what is the size of the global K? Well, in this case, and this is the critical part. So this one you can see that is 6 by 6, and that is because even though the triangle has 3 nodes, every node has 2 degrees of freedom, so that's why you get the 6 by 6 matrix. So the global stiffness matrix is actually 8 by 8. So it's 2 times total number of nodes, and I wrote something. So this is not total number of nodes. This is nodes per element. This is actually 2 times total number of nodes times 2 times the number of nodes. So we have 4 nodes, that's why we have an 8 by 8 matrix. And this is similar to what we did for the trust problem. So here what you would write is, you would write the global node numbers so for element 1, the global node numbers are 1, 2, and 4. So this would be 1, 2, and 4. 1, 2, and 4. But now each of them has an x and a y degree of freedom. So this is, well, 0, 1, 2, 3, or I should do it with the other indexing. Let me do it with 1, 2, 3, 4, 5, 6. But now that depends on, so you can see that now node 1 gets associated with 1 and 2. Node 2 gets associated with these 3 and 4. Actually, this is not correct. This, because these are local node numbers. Actually, let me do it without. I'll introduce this a little bit later. So this is 1x, 1y, 2x, 2y, 4x, 4y. Again, let me do that right here. 1x, 1y, 2x, 2y, 4x, 4y. So here I will have again global node numbers 1, 2, 3, 4, 1, 2, 3, 4, and also 1x, 1y, 2x, 2y, 3x, 3y, 4x, 4y, 1x, 1y, 2x, 2y, 3x, 3y, 4x, 4y. So in reality, and this is, I think, what I was making a mistake before. So 1x is actually 1, 2, so let me use a different color. So 1, 2, 3, and 4 are the node numbers, and then each node number has 2 degrees of freedom. So I'm just using 1x, 1y, 2x, 2y, etc. But actually, if you want to get the indices to put into the matrix, this will be 1, 2, 3, 4, 5, 6, 7, 8, because you have these 8 entries. So 1, 2, 3, 4, 5, 6, 7, 8. So this is the, in red is the global node number, but in this magenta color, that's the actual entry in the global stiffness matrix. So here I would put, for 1x and 1y, I would actually get 1 and 2. Let me move this a little bit down. For 2x and 2y, I'll still get 3 and 4, but for 4x and 4y, I actually have 7 and 8. So here this will also be 1, 2, 3, 4, 7, 8. So what that means is that these are easy. So for example, well, all of this, so all of this part of the matrix, all the part actually just gets moved here. But then, well, in this part of the matrix, so this 7, 8, 7, 8, that one is just this corner, 7, 8, 7, 8. And then this part right here, that part has goes to 7, 8, and 1, 2, 3, 4. So that one goes to this block right here. And this part right here has 1, 2, 3, 4, and 7, 8. So that one is this one right here. And hopefully this looks a little bit similar to what we did for the 2D truss problem. So even though we have 3 nodes, every node has 2 degrees of freedom. So if you remember, what the mapping that we did is 1x actually goes to, so 1x actually goes to 2 times the node, the global node, in this case minus 1. So if I do 2 times the global node minus 1, then I get 1x. So for 1y, I will also do 2 times global node. And in general, so for 2x and 2y, if I want the index, so this will be the actual index, right? So this is the index where they go to. So for any node, global node number, let's say global node ni, that one will go to 2 ni minus 1, that will be the x degree of freedom, and then 2 ni will be the y degree of freedom. I know this is a little bit confusing, and probably the drawings with the shaded area is a little bit clearer, but for the code, what you need to be able to code is this mapping. And what I'll do, because maybe it's a little bit confusing in this format, I will do another part 3 of the video where I explain the code. So I uploaded the code, and you can try to follow the code directly, but I'll do one extra video where I explain the code. But for now, hopefully it is clear that, stiffness matrix for element 1, you can calculate it. So say you did the operations, you get the 6 by 6 matrix, and then in order to do the assembly, you write down the global node numbers, in this case 1, 2, 4, 1, 2, 4. Now each global node number has x and y degrees of freedom, and you want to know where these go into this big matrix. So in order to do that, you can write out global node numbers, but all of them. So in this case 1, 2, 3, 4, 1, 2, 3, 4, each of them with x and y degrees of freedom, and then you can try to do this mapping. For element 2, repeat. So again, you will do this operation for element 2, you're gonna get a 6 by 6 matrix, right? But in this case, for element 2, you have to write out the global node numbers of element 2, and then see where they fit into the global stiffness matrix. So that takes care of the stiffness matrix part. And then comes the force vector. So for the force vector, so that would be part A and part B. I guess this is part B. Then part C is force vector. And so the force vector for element 1 due to the body force, the general definition is going to be the integral over the element of the vector of shape functions times the B vector. But again, if you, and this vector of of shape functions just has well, in this case it has both the x and the y components. So yeah, so this one would have n1, actually it's a 2 by, because it has to go to the 2. So it has 2 rows because one row is for x, another row is for y, and then you have n1, 0, and 2, 0, and so on. And then 0 and 1, 0 and 2, and so on. And then for the triangular element, I gave you a formula at the end of last class that basically writes out the body force vector if, an important if, B is given at the nodes. So if B is given at the nodes, then let me look that up very quickly. What is the definition that I gave you? If B is given at the nodes, then this will be the area of the element over 12 times 2bx1 plus bx2 plus bx3, and then the same but with y, so 2by1 plus by2 plus by3, and then bx1 plus 2bx2 plus bx3, by1 plus 2by2 plus by3, and then 2 more. So this ends up being a 6 by 1 vector. And what you would have to do in this case, B is constant. So in this example, bx1 equals bx2 equals bx3 equals 0. So B is constant everywhere, and we know that the x component is 0, and by1 equals by2 equals by3 equals g h rho, which is gravity times the thickness times the density. So you can plug in the values and then you will get some definition of the force vector for element 1. And it's going to be some 6 by 1 vector. And if you are curious about the numbers, you can open the Python notebook. But this is going to be the force vector for element 1, and what we need to do is the assembly. And again, for the assembly, what you would like to do is you want now this big force vector. Let me make a separation here. So the element force vector is a 6 by 1 vector, and the global force vector is an 8 by 1 because it has to be 2 times the number of nodes. And in order to do the assembly, you would do the same here. You would have 1, 2, and 4, which are the global known numbers associated with element 1, and here you would have all of them. So 1, 2, 3, 4. So here you can see that this one has associated degrees of freedom 1x, 1y, 2x, 2y, 4x, 4y, 1x, 1y, 2x, 2y, 3x, 3y, 4x, 4y. And then actually, again, I'll move this a little bit with respect to again, the problem here is that doing the assembly with this setting is easy. So you can see that this whole first part is gonna go here, and then this one right here is gonna go here, and then I'm gonna have zeros in the other two. So this is easy to see just visually, but actually if you want to code it, what you will need to do is number all the entries here. So you will have 1, 2, 3, 4, 5, 6, 7, 8. So then what you would have here is 1x corresponds to the index 1, 1y corresponds to the index 2, 2x corresponds to the index 3, 2y corresponds to the index 4, 4x corresponds to 7, and 4y corresponds to 8. So again, here, if you do it by hand, you don't really need this index. So this is the actual entry in the vector, whereas this one is global node number. So visually, probably you can do it just based on the global numbers and knowing that each node has an x or y degree of freedom. But in the code, which I'll explain in another video, then you actually need these magenta numbers. And the mapping, as I said, is just 2 times the node number and then 2 times the node number minus 1. Or plus 1, it depends on whether you start numbering from 0 or 1, but I guess that's a minor detail. So that would take care of C and D. So how to calculate the force vectors. Again, you just need to use the formula. So in the code, that's a lot easier, and then for the assembly, you need to be able to match these global numbers and degrees of freedom to between the element and the global force vector. Given that you have that, in this case we don't have any traction force vectors, we only have these body force vectors. So we can set up the system of equations. So what we would end up with is we would end up with a big K matrix, which is going to be 8 by 8, multiplying the displacements. And again, what we will have is it's 8 by 1, and the numbering will be u1x, u1y, u2x, u2y, u3x, u3y, u4x, u4y. And that equals an 8 by 1 vector of, let me call this D. This is going to be the force vector. So this one is going to be an 8 by 1 force vector. In this case, we don't have any traction. So actually, this would just be 8. So this would just be F traction. So in this case, no tractions plus reactions. Also 8 by 1. And now here, we do need to know where do we have reactions. And in order to know what do we have to solve for, then what we need to see is where are the essential boundary conditions. So if you recall the problem, what it says is that we know the displacements at nodes 1 and 2. So those are known. So that means that we can partition the system based on this. So we know all these 4 numbers. So NE equals 4. So we have 2 nodes for which we know boundary conditions, but we know X and Y. So we would partition based on that. So here we would have R1X, R1Y, R2X, R2Y, and then zeros here. And then we have the body forces. And then what you would have here is the same as before. The submatrix that is KE, the submatrix that is KF, and then KEF, and KEF transpose. And that's it. So the solution is the same as always. And that's how it is solved in the Python code. So hopefully that made sense. I think the trickiest part, hopefully, calculating the B matrix for every element is just a matter of looking up the nodal coordinates. The D matrix is just material properties. The stiffness matrix for the triangular element, because you don't need to integrate, just do some matrix multiplications, so you can do that with Python or MATLAB. So hopefully all of that makes sense, and when you look at the code it makes sense. And I think probably the tricky bit is the assembly. So once you have the 6x6 matrix for the triangle, how do you assemble into the global stiffness matrix, which in this case is 8x8 because we have 4 nodes total. Visually it might be a little bit clearer, but for the code what you need to be able to calculate is, what is the number associated with 1x, what is the number associated with 1y, etc. And that is similar to what we did for the 2D truss, and I'm going to explain a little bit more on the Python code. And I would say that's probably the tricky bit. For the force vector, again, the general definition is this. For the triangular element, I gave you a formula. If the B is given at the nodes, then I gave you a formula that is this 6x1 vector, so you just need to plug in values. And then you will get the 6x1 vector by plugging in the values. And then for the assembly, again, I think that's probably the tricky bit for this one. And then once you have the